Hi, my name's Joe. I write Scala professionally, but this isn't a professional talk per se. This is a Haskell talk, and it's a Haskell pet project. So the background for this is I own a 3D printer, and when you've got a 3D printer, it's fun to be able to sort of make some stuff that you can print. It's fun to be able to design stuff that you can print rather than just printing stuff you've downloaded off the internet. But as a programmer, it's generally not that much fun working in sort of like a graphical CAD package. It's nice not to be using a GUI, but to be writing code, because we're generally better at writing code than we are working in a GUI. And also you get such things as version control, and people who work in graphical CAD packages just don't have version control at all. Now there's already this relatively popular thing called OPENSCAD, which is a programmable CAD framework. So you write code, and it describes objects, and you can print those objects. And OPENSCAD is a CSG-based CAD framework. CSG is constructive solid geometry, and constructive solid geometry means that when you design things in OPENSCAD, you're starting with like simple primitive shapes, like you're saying, give me a sphere, give me a cube. And then you're doing sort of Boolean or binary operations on those shapes. So you're saying, can I take the intersection of this cube and this sphere? Can I take the volume that's sort of common to both? Or you're taking a load of cylinders and rotating them in different directions, and you're unioning them together to make a cross. Or you're like taking one shape, the intersection, and you're subtracting something else from that to make holes in it. This is shamelessly plagiarized from the Wikipedia article on CSG. And CSG CAD works fairly well. Like, there's a lot of neat examples of people who've made really cool things using OPENSCAD. Unfortunately, OPENSCAD's kind of like a case study in why language design is hard. There's just a ton of decisions that have gone into the OPENSCAD language. Like, they decided, hey, let's base the syntax entirely on like old-timey C, and like let's not scope anything, and let's not namespace anything, and let's not have higher order functions, and let's not have data types. And I'm not going to talk about that in depth. There's a really great talk by a guy called Matt Addereth talking at a Clojure conference several years back, where he's using Clojure to produce OPENSCAD code. And he goes into a lot more detail about what he thought the shortcomings of OPENSCAD were. And while writing code to write OPENSCAD's a solution to a whole category of these problems, it doesn't really solve sort of the first one, which is that you're generating geometry, and if you're generating OPENSCAD code, you can't then sort of, I have a really short screensaver time. You can't then go in and like look at that geometry and write code that does different things sort of based on the geometry that you've already generated. You've just got an AST. So my take on this was language design's hard, right? There's a reason why some of sort of the most famous, the most sort of like successful programmers that we all look up to are sort of famous language designers. So designing a programming language for doing CAD may be a bad idea. Designing an API, designing like an embedded DSL for doing CAD may be a much better idea. And I thought Haskell was a good fit for that, partially because Haskell's great. Hopefully don't have to sell at least half of you on that. But also because if you're defining a shape and your code is just designed to sort of produce one output, it means that you can write this in relatively sort of simple sort of entry-level Haskell. You don't have to worry about managing state at all. You don't have to worry about config. Your code is the config. And yeah, Haskell's is a pretty clean language to write EDSLs in. So having, it's going to keep doing that. Having said I want to sort of write a CSG implementation, I'd like to talk a bit more about sort of what that entails. And none of this, by the way, is original. This is all taken from this 2013 paper, but also because this is 2019, and there's a JavaScript library for everything, it's sort of heavily plagiarized from someone's JavaScript implementation as well. Now, the next bit's probably going to be common knowledge for some of you, but possibly not all. So I'd like to go through some basics first. I'd just like to talk about how we can represent 3D objects, sort of printable objects, in code. So suppose we want to make a data type for, that's not the screensaver, and we want a data type that can represent this cube or can represent other solid objects. So what information do we know about this cube? Well, the cube has vertexes, as corners, and those corners are points in three-dimensional space, so we can store them as x, y, z coordinates, or as a sort of three-tuple of doubles. But that's not a sufficient representation of a cube, because those vertexes could be connected together in lots of different ways, and so you need to know how those vertexes sort of plug together to make faces. So you say, we also care about the faces of the object, which are polygons, so which are a list, like an ordered list of the vertexes of that face. And a cube or a mesh will have lots of faces, and the list of the faces that make up the boundary of a shape is actually just a sort of sufficient representation of the shape. So we can just say a shape's a list of faces, where a face is a list of vertexes. I make a sort of simplifying assumption, which is that polygons can be a bit sort of tricky to work with, because you've got no guarantee that all the vertexes in that face are flat. You can have a sort of a curved polygon, and that's not really going to be meaningful because you don't know how that's curved. But you can break any polygon up into triangles, and triangles are a bit easier to work with because they're guaranteed to be flat, and you always know that you're going to have exactly 3 points. Turns out this was a terrible mistake, but we'll get into why this was a terrible simplifying assumption for this use case later on in the talk. So the other thing that you have with a triangle, once you've got your list of faces, that's representing the boundary of an object, but you don't necessarily know, just from the boundary representation, which is the inside or the outside. Now, one solution to this would be, say, you've got a triangle, let's just store a direction with that. Let's store a vector that always points out of the object. But you don't need to do that, because your tuple's ordered. So your vertex, your face rather, when viewed from the front, will have the vertexes progressing in either anti-clockwise or a clockwise direction. And that means that we can store the information about what the front and the back of the face is just in the tuple. And it also gives us this sort of flip operation. So we can take a tuple representing a face, and we can flip it. And if we do that to all the triangles in an object, we sort of take the outside and the inside of that object, and we switch them around, which will be sort of useful later. So we've got a way of representing solid objects now. I alluded to CSG operations, yeah. So let's say we have a cube, and we also have this sphere. And we want to calculate this object, so the intersection of the cube and the sphere, the parts of the two volume that's common to both. And we've got a boundary representation of these, so we know what the surface of these objects look like. Now, the surface of the intersection has 2 halves. It has this bit, and that's the surface, that's just the surface of the cube, but it's only the bits of the surface of the cube that are inside the sphere. And then the other part of the surface of the intersection is this thing. And that's the surface of the sphere, but it's only the parts of the surface of the sphere that sit inside the cube. So that suggests that maybe if we come up with some kind of clip operation, if we can take a surface and then clip that to a volume, then we'll be able to build at least this intersection operation. And it turns out as well that when we combine that clipping operation with the flip operation that I alluded to earlier, the ability to take an object and replace the inside and the outside, that gives us things like subtraction, so we can remove a sphere from a cube. So we want to build that clip operation somehow. And to talk you through how you build that clip operation, I'm going to introduce another data type. And that data type's a BSP tree, or a binary space partitioning tree. So let's pretend we have this rabbit as a mesh. and we select like any of the faces of the rabbit to treat as a root node. Let's say this one on the ear. Well, every triangle fits on a plane, so a triangle can sort of be extended outwards in all directions to make a plane, and that plane will partition just space into two halves, and parts of the rabbit are going to be one side of that plane, and parts of the rabbit are going to be the other side, and we can split the rabbit on that plane, and we can store all of the triangles that were out the front in one down one side of the BSP tree, and all of the triangles from the back down the other side, sort of like so. So that gives us the following sort of data type, where you've got a BSP tree which has a front and a back, which are both BSP trees, and you've got some list of triangles. This was very much sort of coming to Haskell. Hey, let's make all your sort of data structures infinite. Actually, turns out that's a really bad idea, and it's a much better idea to have sort of like an explicit branch, which you know is going to have at least one face in it, because you've got to split the front and the back, and also an explicit leaf, so your data structures don't wind out infinite. And everything winds out, in this particular case, everything's a bit faster if you don't necessarily embrace laziness. So we want to take a BSP tree and we want to clip another BSP tree to the volume of that BSP tree. That's a similar but slightly more complex version of a different problem. And the different problem is just taking a point and saying, does that fit inside or does that fit outside this volume? And rather than trawling through this code, and this code is what that is, that implementation, I'm going to show you that graphically. And I'm going to show you that graphically, but in 2D, because it's easier to visualize things in 2D than in 3D. So in 2D, we don't have a volume, we have a polygon. And we have a point, and we want to say, is this point outside this polygon, or is it inside this polygon? And the polygon is a BSP tree, so the polygon's got a root. And the first question we ask is just, which side of the root face does the vertex fit? Is it in front, or is it at the back? And in this particular case, that the vertex is at the back of that face, so we apply the algorithm recursively, but we apply the algorithm recursively to the back of the tree. So we select like this part of the object, and we ask the same question again. So we're at the front, so we apply the algorithm to the front, and eventually we bottom the tree out. And when we bottom the tree out, the vertex is either at the front of the last, the bottom edge in the tree structure, or it's at the back. And which side it is, that's your point enclosure test. A vertex which winds out the front of the bottom edge that you get to will be outside the polygon. One that's at the back is inside the polygon. Clipping triangles is roughly the same thing, but it's roughly the same thing with one edge case. And that edge case is that sometimes you have a triangle that spans the plane, whereby some parts of it are one side, some parts of it are the other. And in this case, all we do is we split that triangle into 3 smaller triangles, and then you can take the ones that are outside and treat them as if they were entirely outside, the ones that are entirely inside and treat them as if they were entirely inside, and that gives you your clip operation for triangles. So does that work? Earlier I showed you like a Wikipedia example of something, an object that you could build up in BSP using CSG CAD. And this is some Haskell. This is taking a cylinder, rotating it around 3 separate axes. It's taking a cube and a sphere and calculating the intersection, and then it's subtracting them. And this is the shape that you get out. So you can make like a sort of solid body that you can send to a printer and print. That's not wildly interesting, because if you run off your 3D printer as sort of like toy plastic objects that don't do anything, eventually your colleagues complain because your desk fills up with junk. But one thing that is occasionally nice to do in code is to write code where your representation of data looks somewhat like the thing that it is. So you can make an array, for instance, and just in that array store the patterns of the face of die. And you can write some code that takes that array and will take a whole and will translate that whole into the locations of the ones in the array. And that will let you 3D print a dice. And you can do other things, like you can model the logo of one of your favorite programming languages, and you can swap out the face of one of the faces of the die, and you can make a... This is like the one point where I didn't want this to happen. We're nearly back. Yep. You can make a Haskell branded die, or you can do the same thing, but with the logo for a sort of popular functional programming conference. And I've actually run off like a whole load of these off my printer in the run up to this conference, so we're giving them away as prizes for the pub quiz, I understand. And also, like, I've got a load of smaller ones, which I think I've just got a handful of, so maybe just come find me for those.
What's the value for beer?
One die, I've got too many die to give a beer for a die. That's going to end badly. Other things you can do, and this is just sort of like demoing that you can do more practical things. The code for this is not spectacular, but my phone case is Haskell as a 3D printed object. Also, this robot arm, which I'll probably just leave out during the hallway track. So this is a robot arm. There's no actual software on the robot arm, but the robot arm itself is printed Haskell code. You can do things, because you're working in code, you can write code that takes Haskell, compiles it, and returns that as a service, and you can bolt a web UI into the front of that. And this just gives you the ability to sort of like write code in a browser, compile it, and see in sort of semi-real time the result of your code. I don't actually use this because it turns out writing code in a browser, not a lot of fun. I tend to just work in a text editor and, you know, compile stuff and have it split out. But it's nice to know that that's there were you to actually want that. There's another thing you can do, which is that you can take your BSP tree and you can take your operations on BSP trees. And rather than just doing those as like plain operations, you can take a random monad and you can build objects up inside a random monad. So you can write code that never generates the same objects multiple times, that generates random, in this case it's chairs. And earlier I mentioned doing point intersection. And point intersection isn't light years away from like a similar problem, which is just line intersection, which is you've got a ray that could represent a ray of light, and that may or may not intersect an object, and when it does intersect an object, it may or may not bounce off in a particular direction. And once you can do that, once you've got the ability to test if a ray intersects, you can build a ray tracer, so you can spit images out of your 3D prints. So I've got this Twitter bot that generates random chairs and posts random pictures of chairs for Twitter, because that is, in some way, objectively fun. And that's how a lot of these slides were done. Not all of, but a lot of the images in these slides were spat out just in Haskell code, sort of running a ray tracer. So who here is familiar with monoids? I'm assuming a lot, but possibly not everyone. So a monoid is a particular type class that you have in Haskell, and other functional programming languages. And a monoid is an extension of a semigroup. And a semigroup just says you've got some data type, and for that data type, there is defined a binary operation, so something that takes two of it and condenses it down into one value. And the constraint that's placed on semigroups is that they must be associative. So if you were to write out an equation like a plus b plus c plus d, it wouldn't matter where you stuck the brackets on that equation, you'd get the same result. And a semigroup can be extended into a monoid by adding an empty element. And an empty element's just an element that you can add onto either side of something with a guarantee that it won't change it. So there's a simple example of something that's both a semigroup and a monoid is a list, because you can add lots and lots of lists together and still get the same result wherever you place the brackets. And you've also got the empty list, and you can add the empty list onto any other list, and you don't change it. And BSP trees are a commutative monoid, in fact, in a couple of different ways. Under intersection, so you can intersect, you can get the volume that's shared, that's in either of two objects, and that operation defines a monoid, where an empty volume, not having a shape, is the empty element. And also unioning shapes together is also a monoid. And that's useful. It's useful because it gives you a way to take collections, and it gives you an easy way to condense a collection of BSP trees down into a single value. It's generally useful for more data types, because you can then sort of confidently say, I think this should be a monoid, and I can write laws tests against that. But the thing that stops you from doing that with BSP trees is that defining equality on an object is actually a relatively difficult thing to do, because you can have two BSP trees where the triangles are ordered in different ways, or even split in different ways, and you won't be able to use structural equality on those because they represent the same shape, but they don't have the same structure, which breaks your ability to do laws testing, which is a bit of a shame. So further work, what's actually bad about this approach? Well, earlier I mentioned I regretted using triangles everywhere. And the reason for this is if you take this example of a shape from Wikipedia and you render it in such a way that you can see where the faces are, you see you just have too many faces. And that's because every time we do a split operation, we don't then go and say, actually we had both of these faces left in. We can unsplit it. And the reason for that is just that with triangles, it's actually relatively difficult to do. It's quite hard to take triangles that you've split and confidently say these triangles can be merged back together into one triangle. And that's a much easier test when you're just working with polygons. Only when I initially sort of sketched out, let's do this with triangles, I wasn't thinking of that. Other further work, like I said, produce more efficient geometry. There's a really common thing in actual CAD frameworks whereby people draw things in 2D and then sort of extrude that outwards, either with a linear extrude or with a sort of a rotate extrude, so making solids a rotation. And I don't do any of that, and I'd really like to. There's also a handful of neat examples of people using programmable CAD frameworks and using convex hull operations, so just taking a concave shape or two shapes and calculating sort of the tightest possible shrink-wrap surface that will fit around them. And there's this thing called Minkowski addition, which is another monoid that you could define over BSP trees had I implemented it. And that's, imagine you have two shapes and one of them was positioned at every point on the inside of the second, and then you unioned that infinite collection of sets of shapes together. That's Minkowski addition, and that would be pretty nice. Largely as a result of the fact that I don't spit out very efficient geometry, the performance for this is terrible. The performance of the CAD framework's iffy. The performance of the ray tracer is just shameful. The Twitter bot, I have to batch up images in advance and then sort of have it run from a batch of images rather than sort of generate them in real time. So there's work that could be done in terms of performance. And as is true for any software project, and I alluded to earlier, it would be better to have this better unit tested. Code for this is online. None of this is on Hackage, but it's on Bitbucket. This CAD implementation and the ray tracer are sort of separately. The robot arm's separate again, as is the phone case, and as are the slides. Thank you. I think we have
I think we probably have time for one or two questions, if they're all right.
Hello.
Hello, what's your MMT for the union operations?
Okay, so they're actually cheat a bit, because the BSP tree is not really, like, it doesn't actually represent a volume if you've got a completely empty one. It represents a boundary between two regions. So if you say, like, by convention, if something's empty, it's the outside, which makes intersection work, then your intersection's not gonna work. But what I do in the case of intersection is I just create a new data type that's effectively like a maybe BSP tree. And yeah, so you just add another value to your type. It's cheating a bit. Another question?
Sorry, what's the most complex structure that you've seen or implemented in this library?
Me personally, I think it's probably that robot arm, which again is not spectacular because there's a really neat Haskell implementation of a robot arm. It's just nice because it demonstrates that you can achieve a certain amount of complexity. In terms of programmable CAD in general, I'd have a tough time saying. There are a handful of nice implementations of fractals, which I've not gotten around to doing in this framework, but there's no reason why you couldn't.
Okay, thank you very much.